So let's start with module 4 of this course, where we'll be talking about the curvature of surfaces. So the idea is we'll start with the second fundamental form, talk about Gaussian Weingarten maps, and normal and geodesic surfaces, parallel transport, and covariant derivatives. And of course, we would be talking about Gaussian curvature, mean curvature, principal curvatures of a surface. And we'll give just a passing remark on surfaces of constant Gaussian curvatures, flat surfaces, and also surfaces of constant mean curvature and Gaussian curvature of compact surface. So this will just give a talk about for a tiny bit of time, right? Okay. So today, this is the lecture 9 of this course. Right. So we had talked in the previous session, we had talked about the first fundamental form. So in first fundamental form, we saw that we could use it for finding the lengths of curves on a surface and also the angle of intersection between two different curves at any point P vector. And we had also tried to understand some of the uh, mm, concepts regarding what we call as the uh, say isometry, the mapping which preserve isometry, and also equiareal maps where we talked about conditions for which under which we can have even after transformation of a surface we can still preserve the area, right? So for that we learned that the first fundamental forms for both the surfaces should be the same, in order to be able to uh, for for a for an equiareal map, right? And finally, we dealt with the conditions for the conformality of maps, and just gave a passing remark on spherical geometry. So today we'll begin with uh, what we call as the second fundamental form, right? So we start with what is the second fundamental form. In second fundamental form, we want to also understand, apart from this, like we would want to understand how much curved a surface is. So we want to know the quantitative description or information about the curvature of a surface, right? So we saw that the first principle, first fundamental form it doesn't tell us about how much curvature there is in a surface. And right, and so this is where the second fundamental form comes in. And we see that if we have the knowledge of both first and second fundamental forms, then we can construct a surface, uh, a surface till the extent of isometry of R3, right? And by using the second fundamental and as well as the first fundamental forms. So similarly, to the case of curves, if we are provided the signed curvature, then we are able to say obtain the curve to some rigid rotations, right? So that's where both these fundamental forms come into play for a sphere or for a surface, right? So we shall start with the case of that of an oriented surface, and where we had talked about that the normal to the surface would be continuous, right? So that is what the orientability implies, right? So let's begin with the second fundamental form today. So suppose we have a surface patch. Suppose uh, suppose sigma tilde is a surface patch, right, in R3 with standard normal. Standard unit normal and vector. Now, as parameters u comma v of sigma change to u plus delta u and v plus delta v, then we'll learn that the surface moves away from the plane, which is the tangent plane through sigma vector u comma v parallel to a distance parallel to the tangent plane by a distance. So sigma vector u plus delta u comma v plus delta v, then minus sigma vector u comma v and dot n vector. So this is the distance by which it moves. So graphically, what it looks like is that suppose we have uh, this surface here, and we have some point here, right? And somehow we have made a uh, so this is the tangent plane and this is our surface. So this is TPS and this is of course point P. This is our surface S, and what happens is so we have a point here. So this was sigma vector u comma v, and this is our sigma vector u plus delta u and v plus delta v, right? And so the difference between these two is of course this line connecting these 2 points. And of course, it will have some normal vector here, right? Some normal vector to the surface at point this one. So this is our normal vector n. So this is what we are talking about this. So this is the quantity which we have derived here. It just says that how much has the neighborhood point at some finite, it's like almost infinitesimal distance away from the point sigma vector uv. How much has it digressed from the tangent plane at point P, at point this. So P vector is this. So that's what we are computing initially. That's what we are trying to do here. Now what we do is that, so this is the degree of deviation, right, from the tangent plane. So now let's expand the above expression in terms of Taylor series. So in that, what we have is sigma vector u plus delta u v minus delta v is equal to sigma vector u comma v plus sigma u delta u plus sigma v delta v plus half of sigma uu and then delta of u squared plus 2 sigma vector uv delta u delta v, right? And then plus sigma vector vv delta v squared plus some higher order terms. Okay. And we can rearrange this in terms of sigma vector u plus delta u v plus delta v minus sigma vector u comma v, right, is equal to sigma u delta u plus sigma v delta v, then plus half of the same thing delta u delta v plus sigma vv square plus higher order terms. Now, what we know that this normal vector is obtained as cross product of sigma u sigma v divided by the norm of sigma of the cross product. So which means that from here we learn that n vector dot sigma u vector is equal to 0 because it's perpendicular, n is perpendicular sigma u. Likewise, n vector dot sigma v vector is also 0 because of the same fact. Now what we do is take dot product with n vector. So upon taking this dot product with n, what we see that the first term we have on the left hand side sigma vector u comma v dot n vector is equal to, of course, the first term on the right, which is n dot sigma u, will become 0. Likewise, even n dot sigma v is 0 by the property by virtue of n being orthogonal to both sigma u and sigma v. So all we are left with is half sigma u dot n vector and then delta u squared plus 2 sigma uv dot n delta u delta v plus sigma vv n delta v squared plus higher order terms, right? So which we can just keep it as it is, but now we can compactly write it down as half into L delta u squared plus k, sorry, 2m delta u delta v plus n delta v whole squared plus higher order terms. So, and recall that this is the deviation that we are talking about. So it means that the deviation is proportional to squared, I mean the terms in second order in delta u and delta v, right? And so here we have introduced 3 new terms, which were L is equal to sigma uu dot n and m is equal to sigma uv dot n and n is equal to sigma uvv dot n. So these are the 3 terms that we have here. So with this, what we understand is that we can easily express deviation just in terms of three new coefficients. So where the coefficients, right? Now we see that this is very similar. So we see that the expression, so the expression L delta U squared plus 2m delta U delta V plus n delta V squared. This is very analogous. It's analogous to the curvature term that we had in the class on curves. So curvature term, what we had seen that the deviation of a curve from with respect to the local tangent, and it was something which looked like kappa delta t whole square, where delta t is the slight increment in the parameter t. So this is analogous to the curvature term in the case of a curve, right? So what we can see that in its as delta v and delta u tends to 0, which means as it approaches some infinitesimal where delta du and dv will be some infinitesimal quantities. So we see that delta L u del u square plus 2m du dv plus n dv squared. This is the second fundamental form of a surface patch. Right? Just highlight in some other color. So this is what the second fundamental form is. And it resembles the first fundamental form in terms of its appearance, just that it has a slightly different, it has a different meaning, right? And we can define like similar to what we had done for the first fundamental form, we can define a symmetric bilinear form here as well. So we define a symmetric bilinear form on the tangent plane as v vector comma w vector is equal to L du of v vector and du of w vector. So this gives us the component along the sigma u axis. And then we have plus m du of v vector and dv of w vector plus du of w vector and dv of v vector, right? And then plus n dv of v vector and dv of w vector, right? So this is how the symmetric bilinear form is defined on the tangent plane for in the second fundamental form, right? Now going back and like going back to our certain examples to bolster our understanding. So we have we'll start with the same was example that we had done in the first fundamental form session as well. So we have a plane for which the surface patch expression is given as A vector plus UP vector plus VQ vector. And as you recall, P and Q are orthonormal. Right? So now let's determine sigma U is equal to P vector and sigma V is equal to Q vector. And then we have sigma UU is equal to just 0. Sigma UV 0 vector, and sigma this is also 0 vector, and sigma VV is also 0 vector since P and Q are constant, right? Are constant orthonormal vectors. And so which means that if we determine the normal vector to the surface, this is n is equal to sigma u cross sigma v divided by norm of sigma u cross sigma v. And since with this we have P cross Q divided by P cross Q norm, right? And since they are orthonormal, all the norm of cross product is just the product of norms since P and Q are orthonormal. So this is just P cross Q. Now L here is sigma UU dot N. This gives us 0 dot N vector is just 0. Likewise, M is sigma vector UV dot N vector. Here also the same thing applies. We'll have 0 dot N vector. And this also gives us 0. Finally, N is also sigma dot N vector is also 0 dot N, which is 0. So which means that the second fundamental form of a plane. So the second fundamental form of a plane is simply 0. And this gives this gives us some say some prior insight, even if we have not yet discussed it, but it gives us some hint about what this second fundamental form actually implies. Now, if we look at here, so L, M, and they give us some idea about the curvatures, right? So what we see that since all these components are 0, it simply implies that there seems to be there doesn't seem to be any curvature for the plane, which is actually true. So when we look at the diagram here, we see that there is a deviation which is given by sigma minus sigma u plus delta u v plus delta v minus sigma uv dot n. However, what we'll see is for a plane, sigma u plus delta v plus this one minus sigma just gives us a vector in the plane, and if we multiply with the normal to the plane, that's definitely going to be 0, since any vector which is in the plane is of course normal to the normal. So which means that there is no deviation of any sort from the local tangent plane, and which means the curvature is 0. So that is what that's what we understand, get some hint about what the second fundamental form tries to imply, right? Now let's go to second example. And we talk about we do a problem on surface of revolution, right? And as we know, the surface patch is given as sigma uv is equal to f of u cosine v and f of u sine v g of u, right? And we assume that f of u is greater than 0. Otherwise, so they will, if we rotate it, then one something penetrates into the other. The surface, a portion of the surface just penetrates into itself, which is like it does. It's not physically. I mean, it's not physical, so to speak. So that's the reason we impose the condition that f of u has to be greater than 0. Otherwise, so the thing is, it will lead to a negative volume if we do not put such restriction on f of u, right? So this is greater than 0, and for all u, and the profile this one. Just tell me. So, and the profile curve is given by u2 f of u comma 0, right? And it's also its unit speed curve. Right. So when we and so implying that f dot square plus z dot square is equal to 1, right? Okay. So now let's try to determine let's go on to determining the coefficients for the second fundamental form. So you have sigma u is given as f dot cosine v, f dot sine v, and g dot, right? And sigma v is minus f sine v, f dot cosine v, and 0. So we also have sigma uu is equal to f double dot cosine v, f double dot sine v, g double dot, right? And then you have sigma uv is equal to minus f dot sine v, f dot uh, uh, cosine v, and of course 0. And then you have sigma vv is equal to minus f cosine v minus f sine v and 0, right? Now we also determine the normal vector, which is sigma cross sigma v divided by the norm of the cross product. And this gives us so what we have here is minus g dot f cosine v comma the second term will be minus g dot f sine v and the last term would be f dot f cosine square v plus f dot f sine square v. So we can just have f dot f. this divided by its norm. So this we have square root of f dot whole squared right, f dot whole squared plus g dot f whole square, right? And this will give us minus g dot f cosine v minus g dot f sine v f dot divided by, so we can bring out f, which is common to both, so it becomes f then root over f dot squared g dot squared, and this we know is 1. So eventually we have n is equal to minus g dot cosine v minus g dot sine v and then f dot. Okay. Now we need to determine those coefficients. L is equal to sigma uu dot n, and this is equal to minus f double dot g dot cosine square v minus f double dot g dot sine square v plus f dot g double dot. So this gives us f dot g double dot minus f double dot g dot. Likewise for m is equal to sigma uv dot n vector, and this gives us f dot g dot sine v cosine v minus f dot g dot sine v cosine v is equal to 0. Right, and n vector is equal to sigma vv dot n vector, and this gives us plus f g dot cosine square v plus f g dot sine square v is equal to f g dot. So the second fundamental form is f dot g double dot minus f double dot g dot, and we have du whole squared plus 2 into 0, so there is no cross product term, and plus f g dot dv squared. So this is the second fundamental form for surface or revolution. Okay, so now we begin with the Gauss and Weingarten maps. Okay. So our so the way to the goal here is to define the second approach. This will be the second approach to define the curvature is to so another approach to compute curvature or first we'll just to define the curvature of an oriented surface is to consider its unit normal, and which is given by n vector. So, and what we'll see that uh, n varies rapidly near a point at which the surface is highly curved. And varies slowly where the surface is slightly curved. Right. Now, if S is a plane, then of course n remains a constant, isn't it? If S is a plane, then n remains constant throughout. Throughout the plane. And thereby, and this also implies that the curvature should be 0. Now, there is where the idea of Gauss map comes in, right? Gauss map. So what does Gauss map do is uh, uh, it defines n at a point at any point of surface S. So which means that the Gauss map is a Gauss map is a mapping or map from S to the unit surface or unit sphere S2 that assigns to any point P, and just remove this, to any point P, which is an element of S at the point at S, the point n vector p, which is an element in S2, and where np is the unit normal of S at p. So that's what it does, right? So ideally, schematically speaking, so this is how it looks. So we have a surface here and a point sigma vector uv, and we have normal n. So we have this normal n, and of course it's a function of uv. And there is this maps to a sphere is the largest circle, diamond, great circle here. And it will always be pointing from the origin to a point on the surface boundary here. So we have n vector uv. This is the origin. So this is what is the Gauss map. Now, now we have an important point here. The rate at which n vector varies across S is measured by the derivative of g. So the derivative of g is dpg at any point p. This maps from the tangent plane of S at point P to the corresponding cos tangent plane to the normal in the S2 surface, right? So, so this is what it is. It maps from the derivative of G, the derivative of G right to a point to this to a point, or it maps to a tangent plane to the normal correspond to the point in of S, right? So this is what it is. Now, the tangent plane at a point Q vector is an element of S2, is the plane passing through the origin perpendicular to Q. So for like, since we have P here, P vector is good. So it will always, it will map to a tangent plane at a point Q is the plane passing through the origin perpendicular to Q, right? So since Q will be here in S2, so the plane, the tangent plane at point Q in S2 is the plane which will pass through the origin. So given that, say this is a point Q vector on this one, right, on the surface of this sphere, then we will have the, the what we are talking about as some sort of a, wait, okay. So this is what it will be. to resize. So it looks like this n vector is perpendicular. So this is how it will be. So this plane will always pass through the origin in S2. So this is S2. And to distinguish, let's have script S2. So we'll have script S2. So since the tangent plane at a point Q is an element of S2, is the plane passing through so, and it has to pass through the origin, the S2. Correct? So this implies that thus what we see from here is that T at G of P vector of S2. Now it is the plane through the origin perpendicular to Q. Origin perpendicular to n vector, np vector. In other words, the tangent plane itself, TPS. So which means that the derivative of G, so thus the derivative of G is a mapping or is a linear map from the tangent plane of S to itself. Right. So the idea is that we use a Gaussian map to move from the surface to its normal space, right? And which will of course lie on the boundary of a sphere of unit radius. So the if we when we measure the rate at which n varies across S, so the derivative of n will of course lie in the tangent plane, right? Tangent plane uh, of tangent plane of TPS, right? Or tangent plane of P at of S at P. And so so this also implies that we are looking at its derivative in S2 surface, and it will map to on the tangent plane itself, right? And what we see is that given that any point we have Q vector in S2, so the tangent plane at any point Q in S2 is the plane which will pass through the origin uh, perpendicular to Q. So in this case, this is Q, right? So since Q is the normal, so to speak, right? It is a unit vector. So of course, the normal to Q will it will be it defines a normal to a plane, and that plane has to pass through origin because that's where uh, we compute all the determine any points in the tangent space, right? So that's the derivative of Q. In a sense, this TGP of S2 this eventually becomes, since it is the same in both scenarios, so this is just TP of S. It is equivalent to TP of S, right? So that's what it is. So we have dp vector of G from TPS to TPS. I know it takes some time to understand it, but I believe uh, it's worth it. Yeah. Okay, so now we come to a definition. So the definition goes as so the definition goes as let P vector be a point on point of a surface S. Then the Weingarten map WP vector comma S of S at P vector is defined as so it's defined by WP vector comma S is equal to minus of the derivative rate of change of the Gauss map, right? So essentially, the second fundamental form of S at P vector is an element of S is the bilinear form on TP of S given by V vector comma W vector at P of S. This is equal to WP vector comma S of V vector comma W vector where V vector W vector is an element of TPS. So this is what it is, right? And we have introduced this minus sign just because later it comes, it is useful to say contain some other minus sign that it comes, right? Just to reduce, so to speak, the total number of minus signs. And this is also bilinear form, and we recall the property of bilinear form that they are linear in both the slots. And yeah, and then of course, right? So this is the important definition here that we just came to know, that is equal to uh, the Weingarten map of S, which is the rate of derivative of the Gauss, this one, right? And since it maps from any vector on the tangent plane, right? So this is what it's valid for that sense. Okay. So now what we do is we define a proposition here. So the proposition states that let P vector be a point of a surface S right, and let sigma vector UV be a surface patch of S with P vector in its image and let L du squared plus 2m du dv plus n dv squared be the second fundamental form of sigma, right? And then for any vectors v and w in Tp of S, v comma w is equal to L du v vector du w vector plus m du v vector and dv w vector plus du w vector and dv v vector plus n dv v vector and dv of w vector. So this is the some sort of a bilinear form. And let's define why is it true. Okay, so there is a lemma. Before we start, there is a slight lemma here. Small lemma here. So the lemma states that let sigma vector uv be a surface patch with standard unit normal n vector of u comma v. Then n vector u dot sigma vector u is equal to minus L, and likewise n vector u dot sigma v is equal to nv dot sigma u is equal to m, and nv dot sigma v is equal to minus n. Right? So let's look at the proof of this. So since given that sigma vector and sigma u vector and sigma v vector are perpendicular or are tangent vectors, to the surface patch, then what happens is that n vector dot sigma u is equal to 0, and also n vector dot sigma v is 0. Now let this differentiate the first with respect to u and the second with respect to v. Let's see what we have. So the first one will give me n u dot sigma u plus n dot sigma uu is equal to 0. And the second one is n v dot sigma v plus n dot sigma vv is equal to 0. So from here, all that we have is this implies that n dot sigma uu is equal to minus nu dot sigma u. And n dot sigma uu is what we have L, right? So this is L. Likewise, n dot sigma vv is equal to minus nv sigma v is equal to m is equal to n, right? And eventually, let's take any, so differentiate this with respect to v. So what we have is nv dot sigma u plus n dot sigma uv. This implies that n dot sigma uv minus nv dot sigma u is equal to m. And likewise, we'll also have n. This is also equal to minus nu dot sigma v is equal to m, right? So this is the basic proof, so to speak. Right. So with this lemma proof we have done. Now going back to the proposition here. So so it says that point P is be a point of a surface S, and let sigma uv be the surface paths of S with P vector in its image, and let this be the second fundamental form. Then for any uv is an element of TPS, then the inner product of uv gives this form, right? Okay, so so let's just take a look here. So so say when u vector is equal to sigma u, and w vector is also sigma u, then what happens is sigma u vector comma sigma u vector again. This is equal to L du of sigma u du of sigma u, right? Plus, and then what we have is plus m du of sigma u dv of sigma u plus the same, it will, since it's we have the same term both sides, both in both the slots. So you have this one, and then dv sigma u, right? Plus n du of sigma v du of sigma v. So now, as we recall, du gives us the component of any vector along sigma u, and dv gives us the component of sigma of any vector with respect to component along the sigma v direction. So in this case, du of sigma u is just 1, and this is also 1, right? Because sigma u is of course equal to sigma. I mean, the component is along sigma u, and it's just a multiple. So here this is also equal to 1. This one, the component of sigma u along sigma v is nothing, right? It's just, there is no component, they are just orthogonal. So this is 0. Likewise, this is 1 and this is 0. And here both the terms are. So this would be dv. So dv. So here, okay, the argument is du. The argument is du. So this is equal to 0. So all we are left with is L. Similarly, if we carry on this exercise for sigma u and sigma v, and just only write the final expression. So du of sigma u is 1, and du of uh, sigma v is 0, plus m du of sigma u is 1, dv of sigma v is 1, right? Plus du of sigma v in the opposite fashion, so is 0, and dv of sigma v, u is 0, plus n, and dv of sigma u is 0, right? And dv of sigma v is just 1. So eventually we are left only with m. Finally, we have sigma v comma sigma v. In this case, we are left with only n, right? Okay, so now we move a little forward from here. And now let's talk about, say, let sigma vector u naught v naught is equal to p vector. Then with the derivatives evaluated at u naught v naught, we have, so the Weingarten map from W sigma u, and as we recall, it gives us the derivative of the Gauss map. So W of sigma u is the derivative of G along u direction, right? So that's what we have, minus d by du at, of course, u naught, u is equal to u naught, and G of the along u direction. So v naught is constant. Right, so, and as we recall, this is minus d by du, and Gauss map is nothing but just the normal vector at u comma v naught, right? And so this is equal to minus, so it's like we are finding the partial derivative of n with respect to u, so it just becomes nu. And likewise, W along Weingarten map from minus sigma v is equal to, again, now we are finding the derivative of n along vx, so to speak, along v coordinate line. So we have minus dy by dv, and v is equal to v naught, and g of sigma vector v u naught comma v, right? So this is equal to minus d by dv at v is equal to v naught, and you have n u naught comma okay. So when we talk about, say, L, so when we have sigma u comma sigma u, so this is as if we have minus is equal to L, right? And L, as we can see from expansion here, it can also be defined as minus nu dot sigma u. And so this is as if we have the Weingarten map sigma u and just with dot product with itself with sigma u. So this is how we are able to show this thing, right? So there is a corollary here. It states that That is the second fundamental form. Is a symmetric bilinear form. Right? So second point is symmetric bilinear form, and symmetric and bilinearity ensures that equivalently the Weingarten map is self-adjoint. So the way it comes out is what is the definition of a self-adjoint? Right. So self-adjoint states that if we have uh, if AV vector, A is some operator, V is the operand, and with respect to V vector, if under dot product or inner product, it's the same as if V vector comma vector of A vector of if this holds true, then this implies that A is self-adjoint. Right? Okay. So now we'll move ahead and talk about discuss what we call as the normal and geodesic curvatures. What we'll do is I'll just okay. Okay. So we saw that the we can express the curvature even in terms of the normal maps. I mean the Gauss maps, which gives us the normals to a surface, right? And it seems, of course, which is true, that the shape of a surface influences the curvature of curves on the surface as well, right? So, say even uh, so, for example, a curve on a plane or a cylinder can have zero curvature, and but a curve in sphere can never have zero curvature, right? So this is not possible because any line segment cannot exist on the boundary of a sphere, right? So which means that we can also look at how much a surface curves by looking at what is the curvature of curves. What is the curvature of curves on the surface? So it is as if we are looking at the how much a surface curves. This is equivalent to or I should say it. Look at the curvature. It is equivalent to what is the curvature of curves. On the surface. So the goal was to say that the shape of a surface influences the curvature of curves. The surface. Right, and we'll find that we again to do this, that it leads us to the second fundamental form eventually. Okay, so what we'll do now is I'll just copy this text, this particular figure from here. Right. So this, we have this here, and let's assume that there is a curve on the surface like this, and we have the normal to the surface in this fashion. So this is the normal to the surface at this point, and the tangent this to this curve is given by gamma vector dot. Right? And the double derivative of this the double derivative of gamma with respect to the parameter is lies somewhere along this line here, which is of course going to perpendicular to gamma dot. So it has to be this. Right? And let's draw it slightly longer. So this is the n vector. And we have this as the so these are gamma double dot vector. It has component along n as well as a component along this direction. And this direction is perpendicular to gamma dot. This is obtained by n cross gamma dot, right? And we have this as an angle phi, and this is kappa. The component along n is kappa n, and the component along n cross gamma dot is kappa g, right? Okay, and this angle is theta. Fine. And of course, the curve is given by gamma vector, right? So now let's begin with our. So let gamma vector be a unit speed curve. Move everything. On an oriented surface S. Then gamma vector dot is a unit tangent vector, or a unit vector, and is tangent to the curve at or maybe it's also tangent to the surface S itself, right? Now, therefore, hence gamma vector dot is perpendicular to n vector. Right, and n vector is unit normal. So gamma vector dot n vector and n vector cross gamma dot are mutually perpendicular unit vectors. So that's the crux here, right? And right, this is one thing. Now, since gamma vector is a unit vector, then gamma dot gamma is equal to 0, is equal to, sorry, 1. And if we differentiate with respect to the parameter, say t, if it is, that's how it defined, then you have gamma double dot dot gamma is equal to 0 twice. So this means that gamma double dot is also perpendicular to so which means that therefore gamma double dot is expressed is a linear combination of n vector and n cross gamma dot vector. That's how it is. So which means that gamma double dot vector is equal to kappa n vector plus kappa g and n vector cross gamma dot vector. Right. So this is one thing that we have been trying to convey. So this leads us to a definition. So definitions is that the scalars kappa n and kappa g are called the normal curvature and the geodesic curvature of gamma respectively. So what we can clearly see that there is an observation that both kappa n and kappa g changes sign or change sign when n vector is replaced by minus n vector, so on a general, which means that not necessarily orientable, surface only the the magnitudes of kappa n and kappa s are well defined. Okay. So what we'll do is I will close the session today here, and in the next session we'll continue the uh, our discussion on this topic, and we'll talk about parallel transport and covariant derivatives in the upcoming lecture, and then we'll start also our exploration into Gaussian mean and principal curvatures from in the next lecture. So I'll just close the lecture for today.